The hypothesis test may also be classified in various forms. So other way of classifying hypothesis test may be either a parametric test or a non-parametric test. Both the tests may be working with either one sample or two samples. So one sample means we have one set of data, two samples means working with two set of data. And in one sample, we are trying to find out whether the sample has got a particular distribution or not. When it comes to two samples, we are trying to find whether the two samples have similar properties or not. So it can be done parametrically or non-parametrically. Under parametric single sample, it can be t-test, z-test. Under parametric two samples, it can be done for independent sets using two group t-test or upper z-test, or it can be paired samples where we can go for paired t-test. So paired samples means one element of one sample has a pair on the other sample. On the other side, non-parametric side, one sample, it may be chi-square or ks or runs binomial. When it comes to two samples, if you have independent samples, then it can be chi-square, Mann-Whitney, median, ks method. If you have paired samples, then sine, Wilcoxon, McNemar, t-square, all these are available. Okay, that's the basics or various possible things. Now let's jump into the first group where we are trying to test whether the given sample is normal or not. That means it's a Bayesian distribution or not. So first question comes it, why do we need to do this normality test? So this is required to determine whether the sample data has been drawn from a normally distributed population. So with some tolerance, of course. So we need to verify whether the sample from where this is drawn is coming from a population which is normally distributed or not. That's one thing. Second thing is we need to verify whether we have collected the samples in appropriate proportion or not. So if the population is normally distributed and if samples are also normally distributed, then we are very sure that the samples are collected from throughout the population in equal proportion as per the population. So we can be pretty sure whatever tests are done on the sample can be equally inferred with the overall population. Then we know that many natural, psychological, or educational variables are distributed approximately normally. So if you look at say educational variables like marks scored in a class, then on average 50% scoring is by majority of the students. So very few people score 0 marks and almost 1 or 2 or maybe 0 score 100 out of 100. So if you just try to put the distribution and, for this various marks obtained by the students in a class, then most of the time it is normally distributed. Any natural phenomena, if you look at, most of them are naturally distributed. Psychological issues are naturally distributed. Anything. So if any such experiments are to be done, then definitely we would like to work with a normal distributed data. The number of statistical tests usually done such as student t-test and one-way, two-way ANOVA require normally distributed sample population. So we need to make sure before taking up these tests that the data you have is normally distributed. So that's one the reason why we need to do this test. The continuous data follow normal distribution, then we present this with a mean value, and this mean value is used to compare between or among the groups to calculate the significance level or the p-value. So when you are trying to compare two distributions, then it would be ideal if we assume that the two distributions or two samples are normally distributed, and if so, then just compare the means, and if means are same, then compare with the variance. So if mean and variance both match for the two samples, then we can more confidently claim that the two samples are similar. So if our data are not normally distributed, then resultant mean is not representative of our data. So definitely we can't use these means for computing or comparing the two samples. And wrong selection of the representative value of the data set and further calculated significance level using this representative value definitely is going to give wrong interpretation. So before inferring anything, before interpreting about the data through any test, make sure that the data you have is normally distributed. So the normal distributed may be symmetrical or asymmetrical. The central one shows the symmetrical, where the three statistical parameters mean, median, and mode are the same. Mean is the arithmetic average. Median is a central value when the data are arranged in either ascending or descending order and pick the central value, that becomes the median. And mode is the one which is the count. So the particular data which is repeated maximum number of times in the sample. Yeah, that's mode. So if the distribution is symmetric, then all three are equal. And in the left side, if you see that, we call it a positive skew. That means the more thing you can see on the right side, left less is on the left side. So the mode is the peak, and median happens to be on the right of the mode, and mean will come to the right of the median. So if you look from the left to right, then first mode comes, then median comes, then mean comes. On the other hand, if it is negative skew, then from left to right, first mean comes, then median, then mode. So that's a reverse order. So to identify whether the data or the sample is Gaussian or normally distributed, so we can conduct some test on that. And after that, you just compute the values of mean, median, and mode. And then if they are found equal, we can say they are symmetric. If mode, median, mean come one after other, then it is positive skew. If else mean, median, and mode come in the order, then it is negative skew. So there are basically three important tests available for normality tests. The first one is the Shapiro Wilk test. Second one is D Agostino K-square test, and third one is the Anderson Darling test. Now what they are, let's check it. Shapiro Wilk test is a test done whether to identify whether the data sample has Gaussian distribution or not. And here the assumption is the observation in each sample are independent and identically distributed. Yes, of course, that's one of the important property when we work on probability and statistics. We would like to work with independent and identically distributed data sets. So it's assumed that that sample is independent and identically distributed. Then to interpret. So the null hypothesis says that the sample has Gaussian distribution and the sample does not have Gaussian distribution is the alternative hypothesis. And we do have direct functions defined in Python, R, and all statistical programming languages. So in Python, we have instruction or a function called Shapiro. You just pass on the data to that, and that will give us the two results, stat and p. Stat is statistical details and p is the p value. And if p value is less than the significance level, so mostly significance level we use 5%. So if p value we find that it is less than 5%, then the null hypothesis is rejected. Then we claim that the data is not normally distributed. So if p value is greater than 5%, then null hypothesis cannot be rejected, and hence we claim that the data is Gaussian distribution or normally distributed. Then D'Agostino K-square test, again same thing, which checks whether the data sample has a Gaussian distribution or not. So assumption is the same. IID is required for the data, and interpretation, again null hypothesis says that the sample is Gaussian, and alternative hypothesis claims that the Gaussian does not have Gaussian distribution. So we have a Python function normal test. So pass on data to the normal test, then we get a result stat and p. And if p value is less than 5%, then we reject the null hypothesis and claim that the data is not Gaussian distributed. If p value is greater than 5%, then we cannot reject null hypothesis. Therefore, the sample is said to have Gaussian distribution. And finally, Anderson-Darling test. So this also used for testing the whether sample has a Gaussian distribution or not. The same identical assumptions for this also, that the data comes from IID space, and the interpretation also same. Null hypothesis says that distribution is Gaussian, and alternative says that it is not Gaussian. And the function used is Anderson. You pass on the data and it gives the result. So from this result we need to do a little extra work on that, and then we get a p value, and from that again, if p value is less than 5%, you reject the null hypothesis and declare that the sample is not Gaussian. If p value is greater than 5%, of course we can claim that the data is normally distributed or has a Gaussian distribution. So that's about normality test.